A supermassive black hole is not just existing at the center of its galaxy but actively killing it by cutting off its star-forming fuel. This astonishing event is happening 11.5 billion light-years away in a galaxy known as Pablo's Galaxy. For the first time, the James Webb Space Telescope has captured this violent cosmic process in action, shedding light on how black holes can shape the fate of their galaxies. In this video, we'll uncover what's happening in this distant galaxy, why it's so important, and what it reveals about the powerful influence of black holes in our universe. The discovery of galactic death by starvation comes from the James Webb Space Telescope's recent observations of a groundbreaking phenomenon in a galaxy known as GS 101578, or Pablo's Galaxy, located approximately 11.5 billion light-years away. This galaxy is being starved to death by its central supermassive black hole. Now, what do we mean by starvation in the cosmic sense? Galaxies need a constant supply of cool, dense gas to form new stars and continue their growth. When this supply is cut off, galaxies enter a quiescent state, effectively halting star formation. Pablo's Galaxy is experiencing precisely this, a process where its black hole is ejecting gas so forcefully that it cannot sustain the birth of new stars. Webb detected this process by observing rapid winds of gas moving away from the center of Pablo's Galaxy at an astounding speed of 2.2 million miles per hour. To put that into perspective, that's about 1,500 times the speed of a top fighter jet. These winds are strong enough to overcome the galaxy's gravitational pull, effectively expelling the very material needed to form stars. This evidence confirms what scientists have long suspected, that supermassive black holes can actively quench their host galaxies by removing star-forming material. Webb's incredible sensitivity allowed it to detect a dense, cooler component of these gas winds, something that previous telescopes have missed. This denser gas is crucial because it blocks light from the galaxy behind it, acting like a cosmic curtain and giving us a more detailed view of the black hole's destructive power. But why is this discovery so important? For decades, astronomers have theorized that supermassive black holes play a critical role in regulating star formation in their host galaxies. However, until now, we lacked concrete observational evidence to support these theories. Webb's observations of Pablo's Galaxy provide the first solid detection of a black hole killing its galaxy by cutting off the gas supply. This discovery is a significant step forward in our understanding of galaxy evolution and the role that black holes play in it. Furthermore, the discovery challenges our assumptions about the nature of early galaxies. Most galaxies in the early universe are bustling with star formation, churning out new stars at a rapid pace. Yet here we have Pablo's Galaxy, which, despite its massive size, 200 billion times the mass of our Sun, has been rendered dead at a time when most galaxies are teeming with activity. The James Webb Space Telescope's observations of Pablo's Galaxy provide a vivid example of a phenomenon known as feedback in astronomy. Feedback occurs when the intense energy released by a black hole, as it pulls in surrounding material such as gas and dust, pushes that material outwards. This ejected gas is crucial for star formation, and when a black hole expels it, the galaxy experiences quenching, effectively stopping the formation of new stars. What makes this observation special is the unexpected aspect of this quenching process. One might assume that such violent ejections of gas would create chaos within the galaxy, causing its stars to become disorganized and potentially altering the galaxy's overall structure. However, in Pablo's Galaxy, the stars continue to move in a well-ordered fashion, suggesting that quenching does not necessarily lead to structural breakdown. This finding challenges previous theoretical models that predicted a more chaotic outcome, providing new insights into the complex interactions between galaxies and their central black holes. This discovery also prompts a reevaluation of what defines a dead galaxy. Traditionally, astronomers have classified a galaxy as dead or quiescent when it no longer forms new stars. However, the case of Pablo's Galaxy shows that star formation can cease even when a galaxy retains its mass and orderly structure. This raises new questions about the criteria for defining a dead galaxy and suggests that there may be more to a galaxy's life cycle than previously thought. These findings open up fascinating avenues for understanding the early universe, prompting us to ask how and why some galaxies manage to grow to such massive sizes only to have their star formation abruptly halted by their central black holes. The research team plans to use the Atacama Large Millimeter/Submillimeter Array in Chile to further investigate Pablo's galaxy. ALMA's ability to detect cold gas and dust will help determine if any cool, dense gas remains and how the supermassive black hole's activity affects its surroundings. These observations aim to provide deeper insights into the interactions between black holes and their host galaxies and how these relationships evolve over time. But Pablo's galaxy isn't the only known example of a black hole killing its galaxy. There are other instances where similar processes have been observed, reinforcing the idea that black holes can be both creators and destroyers in the cosmic theater. One such case is the galaxy Max, which experiences heating of the surrounding gas, preventing it from cooling to form new stars. These examples, alongside Pablo's galaxy, suggest that the quenching of galaxies by their central black holes might be a common phenomenon, especially in the early universe. The question then becomes, how frequently does this happen, and what triggers it? By comparing these instances, astronomers hope to identify patterns that could lead to a better understanding of the environmental and internal conditions that make galaxies vulnerable to such dramatic transformations. The universe is a vast and complex tapestry, with galaxies serving as its fundamental building blocks. Among these galaxies, supermassive black holes lurk at their centers, wielding an influence that is both profound and enigmatic. These black holes, typically millions to billions of times the mass of our Sun, are believed to play a crucial role in the formation and evolution of their host galaxies. Understanding how supermassive black holes affect galaxy formation involves delving into the intricate dance of cosmic materials. When a black hole actively consumes surrounding gas and dust, it releases an immense amount of energy, which can lead to various phenomena, including the creation of powerful jets and winds. These jets can extend far beyond the host galaxy, interacting with intergalactic medium and influencing star formation in neighboring galaxies. One of the most fascinating aspects of supermassive black holes is their ability to influence star formation through a process called feedback. Feedback mechanisms can either suppress or enhance star formation, depending on the environment and the state of the black hole. For instance, when a black hole actively consumes material, it generates radiation that can heat the surrounding gas. If this gas becomes too hot, it will not collapse under gravity to form stars, effectively quenching star formation in the galaxy. As we delve deeper into the realm of supermassive black holes, the concept of active galactic nuclei, AGN, emerges as a significant area of study. AGNs represent some of the brightest objects in the universe, powered by material falling into supermassive black holes. As gas spirals in, it forms an accretion disk, heating up and emitting vast amounts of radiation across the electromagnetic spectrum, from radio waves to gamma rays. This intense energy output can outshine entire galaxies, allowing astronomers to detect these black holes even at great distances. Furthermore, supermassive black holes may also influence the formation of superclusters, massive groupings of galaxies held together by gravity. The gravitational forces exerted by black holes can affect the motion of galaxies within these clusters, altering their trajectories and interactions over cosmic time. Ongoing research into gravitational waves, especially from colliding black holes, adds another layer to our understanding. These ripples in spacetime, first detected by LIGO, provide invaluable data about the properties of black holes and the dynamics of their mergers, enhancing our grasp of cosmic evolution. Through these diverse avenues, the study of supermassive black holes continues to reveal the complexity and interconnectedness of the universe. In addition to suppressing star formation, some feedback processes can trigger new star formation under specific conditions. When a black hole expels material through winds or jets, this ejected gas can compress nearby clouds of gas and dust, leading to starburst activity. These starbursts can produce large numbers of stars over relatively short timescales, showcasing the dual role that black holes can play in galaxy evolution. Researchers have also explored the concept of black hole mergers, where two supermassive black holes collide and merge. This event is not only spectacular but can also have significant consequences for the host galaxy. The merger process can lead to the emission of gravitational waves, ripples in spacetime that have been detected by observatories like LIGO. Additionally, the energy released during the merger can further affect the dynamics of the surrounding stars and gas, possibly leading to new star formation or, conversely, to further quenching. The relationship between supermassive black holes and their host galaxies also raises intriguing questions about galaxy formation in the early universe. Observations of distant galaxies indicate that many of them host massive black holes at their centers, even when the galaxies themselves are relatively young. This suggests a rapid coevolution of galaxies and black holes, challenging previous theories that posited black holes formed only after galaxies had matured. One theory suggests that massive black holes may have formed from the direct collapse of massive gas clouds in the early universe. This process could lead to the rapid formation of black holes that could then grow by accreting gas and merging with other black holes. Such a scenario could help explain the observed correlation between the mass of a supermassive black hole and the properties of its host galaxy, particularly the stellar velocity dispersion. Moreover, the environment in which a galaxy resides can significantly influence its evolutionary path. Galaxies in dense clusters may interact more frequently with their neighbors, leading to phenomena like galactic mergers and interactions that can trigger bursts of star formation. Conversely, galaxies in isolation may experience a more gradual evolution, relying on internal processes to regulate star formation and black hole growth. Recent studies have also highlighted the importance of dark matter in shaping galaxy dynamics. Dark matter, which constitutes a significant portion of the universe's mass, does not emit light and is therefore invisible to traditional telescopes. However, its gravitational influence is critical in holding galaxies together and can affect how gas is funneled into central black holes. Understanding the interplay between dark matter, ordinary matter, and supermassive black holes remains a key focus in astrophysical research. As we gather more observational data from advanced telescopes like the James Webb Space Telescope, our understanding of these cosmic relationships continues to evolve. Webb's ability to observe in infrared allows astronomers to peer through dust clouds and investigate star formation regions in unprecedented detail. This capability opens new avenues for studying how black holes influence their galaxies across different epochs of cosmic time. The role of supermassive black holes in the universe extends beyond their immediate effects on their host galaxies. They are thought to be pivotal in regulating the growth of large-scale structures in the universe. As black holes grow and evolve, they can impact the distribution of matter in their vicinity, influencing the formation of clusters and filaments of galaxies that make up the cosmic web. Additionally, the feedback mechanisms initiated by supermassive black holes can play a role in regulating the temperatures and densities of intergalactic gas. This regulation is crucial for understanding the life cycle of baryonic matter in the universe. Observations suggest that some of the hot gas in galaxy clusters may have originated from the energy released by active black holes, hinting at a broader impact on the intergalactic medium. As our observational capabilities advance, the complexity of these relationships becomes more apparent. Upcoming missions and instruments, including future space telescopes and ground-based observatories, promise to further illuminate the roles of supermassive black holes. They will allow us to study more distant and faint galaxies, helping to refine our models of galaxy formation and evolution. In summary, supermassive black holes are not just passive objects at the centers of galaxies. They are dynamic entities that shape the very fabric of the universe. Their feedback mechanisms, interactions with surrounding gas, and evolutionary pathways play critical roles in determining the fate of galaxies. As we continue to unravel the mysteries of these cosmic giants, we gain deeper insights into the origins and evolution of galaxies, ultimately enriching our understanding of the universe itself. These ongoing investigations underscore the intricate interplay between black holes and their host galaxies, revealing a cosmic narrative where creation and destruction coexist. Each discovery paves the way for new questions, ensuring that the study of supermassive black holes remains a vibrant and essential field within astrophysics. What makes these findings so special is the direct evidence they provide for a process that was long theorized but never clearly observed. Webb, with its unprecedented sensitivity and resolution, allows us to see the universe in ways we could only imagine before. By capturing these detailed views of distant galaxies, Webb is not only confirming existing theories but also challenging and refining them. Thank you for joining us today. Don't forget to like, share, and subscribe for more exciting updates.